All right, we're going to look at switching over to some polar coordinates because choosing coordinate systems that work well for the systems you're in is important. There are many symmetries and many situations where your Cartesian coordinates are not the best way to deal with things. So let's take a function. I'll make some function here. Let me start. I'll start by breaking this into polar coordinates. Let's see if I can get these relatively equal in size. So I'm making some angles, trying to make the angles as the same as possible. And so if I have some function, that function can be defined by in between some angles and then in some radial components of those angles. So let me continue making my polar coordinates, right? We'll chop this up into equal radii. Whoops. Let's see if I can keep things semi-equal distance. All right. All right. And so each of these little elemental things here represent an area element. And the area elements all have a little a, right? They'll each have an area that we can find. And of course, what we want to do is we want to do the limit as the number of these area elements approaches infinity. And then we'll do a sum of the area elements. So, right, our area will be the sum of k equals 1 to n of each little area element a sub k's. And if we get ourselves up to an infinite amount of area elements, then we can find the area. And of course, we'll have our function, right, defined over that area. And so this will tell us that we can have some region that's bounded by this function. But now that function is going to be defined by its radius and its angle. Because we're now using position polar coordinates. And so we talk about things in values of r, right? R running along this way, and then angle theta rotating across. And so this change of coordinates doesn't actually change really this function here. What it changes is this part, what we look at as our elements. And it will change our dA part. Because before we were looking at dx, dy, because they gave us units xy. But here we're going to need to get units of radius and angle coming back out. And so what we want to do then is we kind of want to look at one of these elements. So if we take this a sub k element and we blow it out so that we can look at it or expand it. So we get the segment that it's in, and we go all the way out to the akth element. Then this is going to be the radius, r sub k. And if we have some delta r here and some delta theta here, then this is the rk plus delta r minus delta r over 2, and this is rk plus delta r over 2. So we can look at the sector or any sector element, and we can use the radius kind of centered in this sector. We can go half of our delta forward and half of our delta back. And the area of any sector, the area of a sector, oops, let me switch back here. The area of a sector is 1/2 theta r squared. So if we look at our sector pieces here, then in this little delta element that we're working across, this change piece in here, well, that's going to be the area of the large sector minus the area of the little sector. So if we want to talk about the delta A sub k, which piece we're going to need in here, then we're going to have 1/2 our change in theta times our rk plus delta r over 2 squared, that's the large sector's area, minus 1/2 delta theta times rk minus delta r over 2 squared. And that's the little sector in here. So the difference between those two. Well, this becomes just a kind of expansion and collecting of like terms. So I'll factor out the 1/2 delta theta, and then we'll leave behind rk plus delta r squared, so it's going to be rk squared plus delta r over 2 times rk. Let's see about that. I think there's 2 of these. This is squared, right? So I'm going to get 2. I'm going to get rk times delta r over 2. Yeah, so I'm going to get rk times delta r, right? We get it twice, right? The first time through we get rk times delta r over 2. Second time we get rk delta r over 2. 2 of them leaves us with that. Plus delta r squared over 4. Minus this one here, so I'm going to get an rk squared up front. And then in the middle, I'm going to get a negative 2rk, rk delta r. But this is a minus, so that's going to be plus. And then I'm going to get plus, but that's a minus, a plus. So I'm distributing my negative sign, minus delta r squared over 4. So the rk and the rk will get rid of each other. The delta r squared over 4 and the delta r squared gets rid of each other. And then I have 2 rk times delta r. So all said and done, this is going to give me rk times delta theta times delta r. That means in terms of our differential of area, we have the radius we're at times the change in radius times the change in theta. And this is a weird conversion for us because this is the first time our delta has changed into adding a variable. We get this translation from our change in area is equivalent to the radius wherever we're at times the differential in r and the differential in theta. That means when we want to find an area in polar coordinates, if we want to integrate in polar coordinates, so we have some integral in a region in polar coordinates, then in that function in terms of r of theta, then it's going to be from theta 1 to theta 2, from r being some function of theta to r equals some other function of theta of our polar coordinates r of theta, times r again, dr d theta. Let's look at an example of these and how we can work this back out. So let's find a limit of integration in polar coordinates and look at it. So let's integrate the cardioid. So look at a cardioid. R equals 1 plus cosine theta. And outside the circle, r equals 1. So find the limits of integration for integrating f over r theta over the region that lies inside the cardioid, r equals 1 plus cosine theta, and outside the circle, r equals 1. All right, so let me get my circular component here. Let me get 1 and 1 and 1. So we're going to need everything outside of that circle. So that's going to be exclusionary. And then in our cardioid, well, if we remember our cardioids, r equals 1 plus cosine theta. Well, when theta is 0, this is at 1. And then in cosine is good, cosine is 1, so it's going to be at 2. So this is going to start at 2, and it's going to decrease when theta is at pi over 2. So as it rotates to pi over 2, it goes to 1. It rotates to 1. And then it's going to come back to here and back to here. All right? And gets that heart shape. That's why it's called a cardioid. And so we're looking for the area. Change the color of this inner line here. Inside the circle contained in the cardioid. That kind of crescent moon type shape that we'll get from it. And so we're looking at the boundary, and there we'll have a function defined over top of it. So the integral that we'll get from this, or the parameters that we want to get from this, if we look at how we can move functionally across from here, is as we're moving in terms of radius, we're going from a radius of 1 outwards, right? We're going from r equals 1 outwards to 1 plus cosine theta. So that's going to give us 1 to 1 plus cosine theta. And then in the rotation that we have to do, or these boundary points here, right? Well, we have to think in polar terms. So if I slap my polar graph down, this is 0 to 2 pi. And if I think in terms of my cosine function, I'm going from negative pi over 2 to pi over 2. Right? We're coming from here, rotating all the way around to pi over 2. And we're coming from here, from negative pi over 2 to pi over 2. And that follows what's happening with the cosine. And so we can look at this function as r dr d theta.